And I think we'll turn it over now to Tommy Angelini for his talk. So Tommy is at University of Florida in the Department of Mechanical and Aerospace Engineering. He received his PhD in 2005 from the University of Illinois. And Tommy and his team have developed very recently some very advanced sacrificial and support materials and systems for depositing them in 3D. And his talk is entitled Sacrificial and Support Materials for 3D Bioprinting of Complex Structures. Tommy.
Hi, I'm Tommy Angelini, an associate professor at the University of Florida in the Department of Mechanical and Aerospace Engineering. Today I'm going to be telling you about the use of sacrificial materials in 3D printing. In this talk, I'll cover what sacrificial materials are, how well they perform, what are the limitations, and what are the underlying mechanisms that control their effectiveness. Soft materials like hydrogels, cells, biopolymers, and silicones are extremely hard to shape into finely detailed structures. Often these materials require a lot of time to solidify. Sometimes these materials never solidify. Sometimes even when these materials eventually take on a solid form, are so soft that they'll sag under their own weight or spontaneously change under very weak forces. So lots of different strategies in using 3D printing have been employed in order to shape these really important materials. And most of these strategies involve the use of sacrificial inks or sacrificial supports. So a sacrificial material is simply a material that's used in 3D printing to temporarily provide some type of support and then is usually discarded. So, for example, a sacrificial ink can be used in which a structure is made that supports itself and is very strong and robust and is only intended to form the negative of what is eventually going to be kept. So, for example, printing a sacrificial scaffold and backfilling all the interstitial space with a hydrogel would allow, say, a network of channels to be formed after the sacrificial ink is removed. By contrast, sacrificial support materials are often used when structures need to be made 3D printed from materials that are so soft that they can't support themselves for a period of time. So, for example, a scaffold can be printed inside of a support continuum, held in place while in the liquid state for a long period of time as it, say, solidifies or cures or matures, and the surrounding support material can then be removed, leaving behind a self-supporting structure. Later in this talk, we'll see reasons that we may want to actually leave the 3D printed object inside of the support continuum. There are lots of different types of sacrificial inks and support materials that have been developed over recent years. Some of the most commonly found sacrificial materials include packed concentrated micelles, polymer network with weak reversible bonds, and jammed granular particles. And in all cases, the real idea here is that either these materials can go through very large rheological changes with very small changes in forces or temperature or something, or another way to think of these is that an printing nozzle can be inserted in these materials and moved around, leaving behind a trail of ink to create a 3D structure. Here we have an example of what 3D printing looks like inside of one of these sacrificial support materials. In this case, it's granular scale microgels, which my co-authors and I call liquid-like solids. So here's a time-lapse video of a structure being created. you're seeing straight through a transparent bath of packed jammed granular microgels. These materials are soft enough that the printing nozzle can move in a smooth path, creating structure. This needle is leaving behind nothing more than a trail of unconnected colloidal microspheres. And what you're seeing is the creation of a stable, high-resolution structure that could not support itself at all without the effects of the sacrificial support material. This approach allows sharp corners, nested structures, very thin walls, smooth curves, all to be made out of materials that have no physical integrity themselves. This ability to support structures that can't support themselves is what allows things to be achieved that seem almost impossible, like 3D printing a hollow tube tied in a knot on itself out of nothing but colloidal microspheres that then are trapped in space in this structure. The transparency of this medium allow the details of the printing process to be studied thoroughly by mounting a printing system on the microscope. And so in the lower left, we see we're looking straight up the barrel of a printing nozzle, moving to the left, and we see the sacrificial granular support material dyed with green particles moving to the right, and a trail of red material being left behind, representing a filament of printed structure. So how is it that this material can trap objects in space stably? The way these granular microgels work can be understood by thinking about what something most of us are familiar with, which is hand sanitizer. If you go down the aisles of a CVS or a drugstore and look at the bottles of hand sanitizer on the shelves, you'll notice that there's always bubbles trapped in the bottles of hand sanitizer. And those bubbles weren't just put there. They've been there for a long time. And you might think that they're there because the material is so viscous. But in fact, when you rub hand sanitizer in your hands, it doesn't feel very viscous. You can think of materials like corn syrup or molasses that's far more viscous, but you've never seen bubbles trapped in molasses on the shelf. But what's so special about hand sanitizer that enables it to trap bubbles in this strange way? The answer is that hand sanitizer is not a viscous liquid. It's actually a solid. It's a very, very soft solid that can be yielded and rearranged and broken with very, very weak forces. And those bubbles don't rise because they can't generate enough force to yield the material. And what gives this material this special property is that it's actually made out of microscopic hydrogel balls that are all packed together in a jammed state. And when this material is yielded, those balls are rearranged, temporarily fluidized, and when a force is removed, those balls pack back into place and the material turns back into a solid. Now, this principle of yielding and resolidification is something we're all familiar with. We've seen it all the time, and if you take a child to, say, a Chuck E. Cheese and watch them in a ball pit, that's exactly how this material works. The child can lay on top or inside of the ball pit, sitting still, totally supported. But as soon as the child starts to swim around and exert forces that cause the balls to yield, the child can swim. Now, in our case, instead of hard plastic balls, we've got microscale or granular scale hydrogel particles filled with solvent. And instead of a child, we are leaving behind cells, biopolymers, colloids, hydrogels, et cetera, and creating structure that's just trapped in space the same way the child's trapped in space. Often, it's desirable to 3D print an aqueous ink inside of an aqueous an aqueous support material, and the fact that the ink and the support often share the same solvent leads us to question whether we can maintain control, whether we'll get mixing between ink and solvent. One way to test this is to ask, does 3D printing inside of a sacrificial material follow a very simple manufacturing principle, which relates the material deposition rate coming out of the nozzle with the nozzle translation speed to the diameter of the feature that's being produced. And to generally answer this question, for all the different examples of 3D printing with sacrificial inks or supports we could find in the literature, we collected as many examples as we could and created this sort of manufacturing chart to ask whether this really simple principle of volume conservation and feature size is followed. And in these many examples, we find that in general, it is followed. One can predict the cross-sectional area of a feature, whether it's a filament or a droplet or deposited in any way. One can predict the average cross-sectional area of that feature by taking the ratio of the material deposition rate, the flow rate of material coming out of the nozzle, and the translation speed of the nozzle. So there is a manufacturing principle that allows for predictable control using sacrificial inks and sacrificial support materials. These same data can be broken down into a slightly higher dimensional manufacturing chart in which we plot the material deposition rate versus nozzle translation speed on a logarithmic scale. And choosing targeted feature sizes creates the diagonal dashed lines, allowing the constraints on material deposition rate and translation speed to be identified to achieve a certain feature size. For example, if I wanted to 3D print an object with a total volume of 1 microliter in 1 hour, and I wanted to achieve a feature size of 10 microns, I could do that by translating my nozzle somewhere between, let's say, 1 and 10 millimeters per second, an easily achievable target. Or if I wanted to make an object that's 1 milliliter in size at that same high precision feature size, that same high resolution feature size, I'd have to move my nozzle at about 1 meter per second, which is much harder to achieve and hasn't yet been achieved. And further, if I wanted to make an object the size of a liter, like a body part size object, or this bunch of grapes, for example, doing that at a 10 micron precision is off of this chart. In fact, even at a resolution or a feature size of 100 microns, I'd have to move my nozzle at about 10 meters per second, which no machine has yet achieved. And here we demarcate a region of unexplored manufacturing space that is achievable by current machines and lies where a lot of biofabrication is needed, where we need high fine feature sizes and performed at short times. It's clear that to create large objects with fine features, one of the direct paths forward is to move injection nozzles quickly. Unfortunately, moving injection nozzles quickly introduces a type of instability. We've surveyed many different types of instabilities that occur in soft matter manufacturing. In the upper left, we have an illustration of an inertial instability, a Reynolds instability, in which fluid starts to recirculate and printing becomes less smooth. In the upper right, we have a crevice formation, which results in materials that are essentially too stable. On the lower left, a common instability is gravitational sagging, which I'll address later. And on the lower right, when immiscible materials are used, when the ink and the support material have a large interfacial tension, feature breakup can occur driven by interfacial tension. To investigate potential limitations of 3D printing into sacrificial materials at very high speeds, a rotating drum test apparatus was developed, allowing nozzle translation speeds exceeding 1 meter per second, which is much faster than most current printers can achieve. Two different instabilities were observed to emerge. One was a dynamic crevicing phenomenon in which an air gap opened near the surface of the sacrificial material, then followed in the wake of the injection nozzle. The other expected instability that occurred was a Reynolds instability, in which the injected ink went from a smooth, laminar, hydrodynamically reversible behavior into a recirculating, mixing, unpredictable behavior above Reynolds numbers of somewhere around 3 to 7. A different type of instability has been observed in an approach designed for 3D printing silicone. In this example, a organic-based microgel system, micro-organogel system, a sacrificial material, was used to support silicone structures as they cured during 3D printing. It was found that a minimum feature size existed, below which features were unstable and would break up under the interfacial tension between the ink and the support material. And the higher the yield stress of the surrounding material, the finer the feature that could be achieved, unstable features would last before breaking up. The extremely low yield stress of most sacrificial materials creates the possibility that a printed object supported by a sacrificial material may rise or sink after printing. This instability was explored and tested by placing spheres of many different densities and sizes inside of a sacrificial support material, many different sacrificial support materials having different yield stresses. What we see here is the red data points were all unstable, meaning they either rose or sunk, and the blue data points are stable, meaning they were well supported by the sacrificial support material. And the black line is a theoretical prediction based simply on density mismatches and gravitational forces. This observation allows you then to predict the largest object that could be supported given a density mismatch. So for example, 3D printing material with a density of bone is much more limiting than, say, 3D printing material with the density of muscle or fat. All of these instabilities are largely controlled by the rheological properties of the sacrificial support materials used. While simple models of viscoelastic materials don't capture all the richness of these complex fluids, they do serve to allow us to categorize and contextualize the observations or the behaviors that we observe in these sacrificial materials. The two kind of extreme models for viscoelastic materials that are useful to think about are Maxwell materials and Kelvin-Voigt materials. One can think of a Maxwell material as a high-frequency solid and a low-frequency liquid. One can think of a Kelvin-Voigt material as a low-frequency solid and a high-frequency liquid. Here we lay out the elastic moduli, G prime, as a function of driving frequency, and the viscous modulus, G double prime, as a function of driving frequency for these two models. And one can see that for the Maxwell model at high frequencies, G prime is larger than G double prime, and vice versa for the Kelvin-Voigt model. And of course, the converse occurs at low frequencies. This has significant consequences because when 3D printing with soft materials, if the material itself is under a small yet persistent force, that corresponds to the low frequency limit. And if the support material acts like a liquid at low frequencies rather than a solid at low frequencies, it may not be able to support a three-dimensional structure for very long. One way to understand how a sacrificial 3D printing material will resist persistent forces is to measure the shear stress required to shear it at a certain rate. These shear stress versus shear rate curves really reveal the differences between these materials at low frequencies. For example, the Newtonian fluid, the stress in a Newtonian fluid is simply proportional to the shear rate, whereas in a shear thinning fluid, that stress depends sublinearly on the shear rate at high shear rates. And in yielding solids, even in the limit of low shear rate, of zero shear rate, the material can withstand a finite stress. So these types of curves help to classify and categorize different types of materials. Sacrificial materials used in 3D printing that can be described as yielding solids include jammed granular particles, whereas materials that act like shear thinning fluids include, say, entangled polymer networks or some weakly bonded polymers. One way that sacrificial 3D printing materials are commonly characterized is to measure their elastic modulus as a function of strain amplitude, shown in the lower right-hand corner. A drawback of this approach is that a large diversity of materials will exhibit a similar behavior. In other words, they'll all exhibit a plateau at low strain amplitudes and a drop-off at high strain amplitudes. And this makes shear thinning fluids look just like yielding solids, even though when measuring their frequency-dependent behavior or the shear stress as a function of shear rate, they are shown to be very different. And what this type of test does then is is actually obscure some of the underlying mechanisms and behaviors that one would expect out of a soft material to be used in 3D printing. So caution should really be taken when interpreting a shear modulus versus strain amplitude type test. And a final example of using sacrificial materials in 3D printing, here we have a series of objects 3D printed from living cells. These materials are printed into jammed granular microgels. The movie in the upper right, in the movie in the upper right-hand side, we have a 3D printer mounted onto a microscope. The microscope is looking up at the nozzle, and as the nozzle moves around, it leaves behind a trail of cells that are trapped in space, just like the colloids were in the examples shown earlier. A whole host of fine, intricate structures have been 3D printed, from crosshatch scaffolds to cloverleaf lemniscates to these small loops to even kind of rugose magic carpet-like manifolds floating in space. This object rotating in the lower left was printed out of cells and then imaged at very high resolution. And with this approach, this wavy manifold could be printed as thin as 3 cell diameters. So high-resolution bioprinting within sacrificial materials, like jammed granular microgels, has been demonstrated and has been demonstrated. Now, there's one added benefit to using a sacrificial type material like jammed microgels for 3D bioprinting. And that's that since cellular structures take an extremely long time to mature and form cell-cell junctions and create their own matrix and become robust little tissues, they need to be printed into an environment that can host them and house them and support them for a long period of time. And so extending the maturation time indefinitely means what the sacrificial material becomes is no longer just a sacrificial material. It becomes a 3D growth medium itself. So the jammed granular microgels swollen in cell growth media have been used for 3D printing spheroids and for studying cells in 3D migration and for studying cells proliferating and studying the diffusion of molecules into spheroids, all within this one sacrificial material that was initially intended only to support 3D printing. So I'd like to thank you for your attention and acknowledge my co-authors above and the funding below. Thank you.
Great. Well, thank you very much, Dr. Angelini. That was a great session. And now we have you live for Q&A. Very exciting. Just a reminder, if you have questions, please enter them in the question tab, and we'll get to them as soon as possible. So the first question has to do with really I guess the compromises that may need to be made in terms of a bioink between, its printability and also cell viability. And I know you addressed some of these aspects in your talk. So do you think the ideal bioink has been achieved? And if not, what kind of innovations are still needed in this space?
First, thank you for having me. I really appreciate being invited to participate. The question of a bioink, I think, it really depends on the type of bioprinting we're talking about. And a lot of what I talked about in my talk on sacrificial supports, most of the time, at least from my perspective, I'm viewing my cells as the bioink, and this support as simply very gently cradling them, and so we never have an issue of viscosity or shear forces rupturing cells. Our bioinks truly are nothing more than essentially pellets of cells mixed with matrix precursors. And after we print, let's say, collagen type 1 monomers will polymerize and surround the cells, which then spread out and grab on and do their thing. So there's no real major viscosity problems there. Now, I think there's another side of this view on printability of bioinks, and it's really a question of what the mechanism of printing is. Some printers are pressure-driven, and some pressures are displacement-driven. So even an extremely viscous material can be pushed through a very fine nozzle if you have a displacement-driven system that is essentially infinitely rigid. It's when you have a pressure-driven system that printability of viscous materials becomes a huge challenge. And then finally, a lot of these bioinks, even though we view them as being very viscous, or even though they are very viscous, and potentially can apply large shear forces to cells if they're sheared, a lot of these materials, when flowed through a channel or a nozzle, actually flow in plug flow rather than in couette flow, and there's very little shear transverse to the flow direction. So personally, I think if there are problems with viability, a lot of careful studies that directly measure and demonstrate the shear profile in these systems should be done. And I think there's a lot of room for careful, fundamental kind of microfluidic type studies to be done that inform us about bioprinting processes. And so,
sorry. Go ahead.
Just to close, do I think we're anywhere near an ideal bioink? No, other than saying that, in my view, the best bioink is nothing more than cells and matrix.
Well, that's great. So it seems to be sound then, at least in part, the support, the sacrificial granular support materials is one way to get around the need for optimizing bioink viscosity in the case of when you would print in air. I guess in these support bath materials, it allows you to, I guess, print a wider range of materials types than even just cells and matrix. I guess maybe building on that, in terms of then that granular support medium itself, how do you think that can maybe be expanded further? I know you've done a lot of kind of careful studies looking at how the various properties affect printability, and maybe, where you see that going in the future. Yeah,
so as I alluded to in my talk, I think the goal of high precision, high resolution, printing of large objects is one that is not going to go away, and it's like kind of the holy grail of bioprinting is we want to be able to print a large piece of tissue with very high resolution very quickly, and that means moving fast. Now, I suppose there's another parallel direction that I think is really attractive, and that's somehow learning how to parallelize this type of approach. I can't say how this would be done, but there's unfortunately a kind of disconnect between massively or highly parallel methods using like SLA type methods or clip or holography, and then approaches that use these kind of sacrificial supports. And I think somehow a hybrid between these two is going to be eventually may give us a path forward for achieving large objects with a high precision. I don't know how, but I can't foresee, based on the instabilities in the fluid dynamics, I can't foresee how we're going to achieve what we need to achieve just dragging nozzles around in space.
Okay, thank you very much. So we've got a couple questions that are a little bit more, I think, about the printing process and on the hardware side. Maybe you could comment on these, really around the ideas of how do we print, and I think you kind of touched upon this a little bit just a second ago, but how do we print multiple materials and cell types in these systems?
Yeah, so there's a lot of opportunities. I mean, if you Google like bioprinting on YouTube or something, and you see all these various, commercially available bioprinters, the way it's often thought of is I have one syringe or one container filled with cell A, another container filled with cell B, another container filled with cell C, and some matrix or whatever, and my robotic arm or my gantry system can go around and pick up the container, whether it's a syringe or some other container, and then print and then put it down and pick up another one. That's the most common way I've seen people envision multiple cell type, multiple materials and multiple cell types. We've recently sort of, in the case of sacrificial materials, though, because there's a finite hydrodynamic radius around, let's say, an injection nozzle. So for example, if I'm dragging a needle through most any of these sacrificial materials, the zone around the nozzle that's about one nozzle diameter away is temporarily, let's call it temporarily fluidized. But what that means is I could have another nozzle 2 or 3 diameters away printing something else. And so I think eventually, if we get really good controls and controls theorists and roboticists doing good path planning, we could end up with multiple robotic arms coming in from multiple angles, moving nozzles around in space and sort of tracing back and forth, basically trading places, so that you don't have a single deposition tool in your bath at a time. That's one way to parallelize. Another one is to actually just redesign the deposition nozzle so that you have a system of valves and valves and tubes, so that you can supply different materials and switch back and forth. And I've seen prototypes, but I think that kind of system is I haven't seen available yet.
So actually, I do know on that point there is one commercial vendor, Aspect Biosystems, that is working on a multi-material single extruder head. But to that point, it sounds like there's a lot of, I guess, work still to be done then, kind of on the hardware side in terms of multiple extruders that can be operating at the same time, almost independently in 3D space, right? It sounds like that's
it's hardware,
quite the
also mathematics. I think it's path planning. The idea of optimizing paths in 3D space between multiple agents. That there's a ton of room for engineers to do great things, and it's not hardware in that case; it's software. But yeah, to your point, Adam, the accompanying hardware will have to be made too.
Yeah, so we had a question along those lines, and you kind of addressed it a little bit, but how do you generate the code that controls your 3D printer?
It depends. In my lab, when we have simple structures like, those Russian dolls, we literally write down a formula for like a helical shell with a undulating, envelope. Or if we have to draw a cone that points along a certain direction, we start by making a helical shell cone and then doing a rotation matrix and then writing down those coordinates. And it's all literally just kind of spatial geometry. Now, when you want to do something else like the knot, that we didn't write down a formula that describes that knot, or a lot of the other things. There we go from solid models like SolidWorks or other solid model generating software, and we do what everybody else does, which is turn it into G code. And G code is just a series of commands with basically points in space and instructions for how fast to move that most 3D printers, especially the hobbyist type printers, read. It's also what most of our automatic machining systems use. So either so G code or just manual sort of mathematics.
Excellent. So when you're printing cells, and really in bioprinting in general, it's a living material. It's going to change over time, and some people have called this 4D printing for stimuli responsive materials. But can you comment on kind of the fact that you have a living system that is going to be actively remodeling its environment, how that impacts kind of the design strategy when you want to make something with 3D bioprinting?
Yeah, and in fact, that's directly where my lab is headed at the moment. It's an interesting question because you're creating very, very small scale structures out of very, very soft materials, filled with objects that want to exert forces, and those are the cells. And so if I create a microbeam out of collagen and I fill it with cells, that microbeam may do things that macrobeams do when they're under large loads. That microbeam may buckle. That microbeam may exhibit all of the different sort of mechanical continuum elastic behaviors that we know on the large scale. And we don't know how to predict those things, and we don't know if our large scale kind of continuum models will do the job for understanding and predicting what these small scale objects are going to do. I think it's an amazing direction to go for fundamental studies, and I think what we learn there is going to help guide us for design, because it says if you make a beam too thin and too long with too many cells and they contract inside of it and that causes that beam to buckle, and you don't want a buckled beam, you better figure out how to mitigate that problem and design ahead of time so that you prevent those instabilities.
Okay, great. Thank you. Well, maybe we'll just end with a question that's maybe a little bit more big picture. And just want to get your thoughts on what some of the maybe both near-term and maybe long-term examples of where you think 3D bioprinting is going to make an impact, either clinically or more just science and technology, but something kind of more in the real world, everyday application or more specific.
Yeah, I think just over the last, I'm not the first to say this, but I do see this trend emerging, which is instead of going for that big holy grail printing a functional organ. A lot of groups are starting to try to print small-scale objects and use this tool as what it really is. It's a nice manufacturing tool. So if I could create a small microtissue that is very reproducible, and I can create many of them in very short time and keep them alive because they're very small and they don't need vasculature, then maybe I can use those objects to, say, test for the efficacy of drugs or something like that. And that strategy is taking off. I see it more and more. Even companies like Organovo are taking similar strategies. They're trying to create little liveroids that they can use to test for liver toxicity of drugs, so I see that whole direction as being having a huge immediate impact, and I think it's achievable because if you think about it, what are the biggest challenges and limitations of bioprinting when we think about traditional bioprinting, where we try to print functional tissues and organs? It's vascularity, and it's the inability to make things very large very fast. And making microtissues that have the essential properties of a tissue and respond minimally in a faithful way that represents what happens in vivo without needing vasculature solves both of those major problems in bioprinting. And so I think we have a really great future in the next 5 to 10 years with microtissues.
Yeah, I mean, I totally agree, and I think that's a really exciting area. I think the future is definitely bright, both in the near term and hopefully in the long term with continued innovation and maybe expanding that to larger scale constructs eventually, so that we can do some regenerative medicine too. Mm-hmm. Well, Dr. Angelini, I want to thank you very much for participating, both your talk and the Q&A session, as well as Dr. Galinsky and David earlier for asking questions.